Good morning to all of you. Today we are studying physical property and molecular structure. Additive property are those properties whose total value is equal to sum of individual constituent particle or atoms. For example, molecular mass. Consecutive property has those properties whose values depends upon structure and arrangement of atoms like optical activity, surface tension, viscosity, etc. Additive and consecutive property. These are those additive properties whose depends upon the arrangement and bond structure of atom in a molecule. For example, viscosity, surface tension, etc. Plane polarized light. A beam of light having vibration only in one plane is called plane polarized light. In figure 1 we can see ordinary light which have vibrations in all the direction, and in B there is a plane polarized light which have only vibrations in one plane. Optical activity. The substance which rotate the plane polarized light are called optical active substance, and this property is called optical activity. Those substances whose rotate the plane polarized light to right are called dextrorotatory and written with a sign of plus, and those substances which rotate the plane polarized light towards left are called levorotatory and written with a prefix of negative sign. Polarimeter. Polarimeter, as we can see in figure 2, this is a polarimeter placed in front of a source of light. Polarimeter contain a polarizer, analyzer, and a sample tube. Polarizer is placed in front of a source of light that provides us a plane polarized light. Then a sample tube, we place the sample in the sample tube, and by the help of analyzer we note by what angle the plane polarized light is rotated by the sample. The principle of polarimetry is when the polarizer and analyzer are placed with their polarization plane parallel to each other, the plane polarized light emerging from first prism passes through the second and bright field is obtained. But if the second prism is rotated by 90 degree, then the coming out of first prism are stopped by the second and the dark field is seen. As we can see in figure 3a, the analyzer and polarizer are in the same plane, so the bright optical view is observed. And in figure B, the plane of the angle between polarizer and analyzer is perpendicular, that's 90 degrees, so dark spot is obtained, and when they both are at some angle, some shaded portion is observed. The factor affecting the angle of rotation. The angle of rotation is affected by nature of substance, nature of solvent, concentration, temperature, length, and wavelength of light used. The angle of rotation is denoted by alpha, is directly proportional to length into mass by volume. And the cons and for to remove the sign of directly proportional, a constant is used called specific rotation and is denoted as shown in equation 3. T is the temperature and lambda is the wavelength of light used and called specific rotation. Specific rotation for solution is 100 into alpha, that is angle of rotation, divided by length into concentration. For pure liquid and solid, that is equation 6, is equal to alpha by length into density, depends on density. For pure solids is same as liquid. And for molar rotation, that is specific rotation is multiplied by molar mass but divided by 100. Measurement of angle of rotation. To measure angle of rotation, polarizer is used as shown above. The angle between polarizer and analyzer is measured as shown in figure 4. The sample is placed in sample tube, polarizer, light comes from polarizer, passes through the sample tube and then by analyzer, and by rotating it to observe a complete dark phase, the angle is measured. Optical activity and molecular structure. Optical activity is a consecutive property, so it depends on the arrangement of atoms around it. Normally, the compounds which have chiral carbon atom are optically active. Like as shown in lactic acid, the carbon is asymmetric carbon arranged with four different atoms, so it's optically active. Or generally, optical activity are those substances which have non-superimposable mirror images, and these images are two isomers called isomers, in which one is electrorotatory and other is dextrorotatory. The non-superimposable images are called enantiomers. An equimolar mixture of enantiomers is called racemic mixture, which have net zero angle of rotation due to cancel out of angle of rotation of each other, and that mixture is called angle of racemic mixture. The separation of dextro and linear forms is called resolution. Some compounds have mesoform and are optically inactive, but they still have chiral carbon atom. As we can see in mesoform of tartaric acid, the yeast has two chiral carbon atom but has a plane of symmetry. That's why it's optically inactive, and this is the reason of why mesoform are optically. As a result, meso compounds is optically inactive. Here are some examples for calculation of specific rotations. Here are some problem type questions for the solving of for students. Dipole moment and polar and non-polar covalent bonds. The bonds formed between identical atoms are non-polar bonds because they don't contain any pole due to same electronegativity of different. Or polar molecules are those molecules which have poles or are formed by different type of atoms which have slightly different electronegativity are called polar covalent bonds. As we can see in HCl, the electronegativity of H and Cl are different. That's why they create us slightly charges on both of them, slightly positive on H and slightly negative on Cl. It's polar, and as seen above, H between same type of atoms formed bonds like H2, HH, Cl2, CaCl, FF, F2. They have same atoms and same electronegativity. That's why they don't generate any slightly charges or charges over them. They have different same electronic forces. That's why they are called non-polar bonds. Dipole moment, a measure of degree of polarity. Dipole moments gives us the idea about the polarity in a covalent molecule. It is defined as a product of magnitudes of charge and the average distance of separation between the charges, that is between the two nuclei, denoted by mu. As seen in above formula, mu is the dipole moment, q is the charge, and d is the separation between two nuclei. The units for dipole moment in CGS, it's one dipole is equal to 10 raised to power minus 18 ESU centimeter, and in SI, one dipole is equal to 3.336 into 10 raised to power minus 30 coulomb meter. Dipole moment is a vector quantity and represented as shown below by the arrow with a tail. As seen below, dipole moment shown downside. The slightly positive side is marked towards tail, and arrow is marked towards slightly negative. Dipole moment of polyatomic molecules. As we already studied dipole moment of diatomic molecules, but here are some polyatomic molecules like AB2 type. Their dipole moment is found by the formula mu is equal to 2 mu AB cos phi by 2, that is net dipole moment. The contribution of individual dipole moments of bonds AB and AB gives the total bond moment. The net dipole moment of the polyatomic molecule is the resultant of different bond moments. For a molecule of type ABC, the net dipole is mu is equal to under the root mu1 square plus mu2 square plus 2 mu1 mu2 cos theta. Theta is the angle between two bonds. Here are some bond moments given in the table of diatomic molecules. Group moments. The dipole moment of some groups like NO2C and OH, they are determined and are called group moments. Polarization of molecule in an electric field. If when a non-polar molecule is placed between electric field, it generates some dipole, and that's called induced dipole, and that polarization is induced polarization. This is termed as polarization or distortion of molecule. The molecule is distorted in the electric field to induce dipole. It is represented as mu I is equal to q into d. Q is the charge, D is the separation, and mu I is the induced dipole. Mu I depends on the strength of applied field and is directly proportional. To remove the sign of directly proportional, a constant alpha is used called as polarizability of molecule. The magnitude of alpha depends on the dielectric constant. Induced dipole polarization is of three types. Electronic polarization is due to displacement of electrons to the position of nuclei. Atomic polarization is the polarization induced due to distortion of nuclei, and orientation polarization is the polarization induced due to of polar molecules which have different orientations in the applied electric field. Alpha E is used to represent electronic polarization, alpha A is used to represent atomic polarization, and alpha O is used to represent orientation polarization. For polar molecules, it's is the combination of all the three is the total polarization, but for non-polar molecules there is no orientation polymerization, so its total polarization is equal to distortion polarizability, which is the sum of electronic polarization and atomic polarization as shown below. Clausius-Mostry equation. It gives a relationship between distortion polarizability and dielectronic configuration. As shown in equation 4, is E naught is equal to E plus 4 pi I, and I can be noted as mu I into n number of molecules per unit volume. He placed some non-polar molecules in the dielectric field which induces dielectric. Divide equation 4 by E and put E naught by E is equal to D, which is dielectric constant. We found the equation 6. E naught is the field strength of the charged plates, minus 4 pi I is the charge induced on the surface of dielectric in contact with the plates, and 4 by 3 pi I is the charge induced on the surface of spherical cavities. And by solving as shown below, we find a equation number 13 called as Clausius-Mostry equation, and equation 15 and 16 are also the form of Clausius-Mostry equation. Dipole moment and molecular structure. Dipole moment and molecular structure is used in comparison of degree of polarity of in molecules. For different type of molecules, their polarizability can define us the charge over them. We can find their ionic character. More the dipole moment induced, more is its ionic character. Where ionic dipole, we can find ionic dipole and then compare it with the observed dipole moment divided by dipole moment into 100 is gives its percentage ionic character. Shades of molecule. Diatomic molecule always linear irrespective to the value of their molecule. Polyatomic molecules dipole moment not depends upon the individual dipole moment of the bonds but also on the spatial arrangements. For a polyatomic molecules, it's not on the single bonds dipole moments, it also depends on both bonds molecules. For a triatomic molecules like CO2, the next dipole moment is 0 due to cancel out. But there are some triatomic molecules like H2O, they have angle not 180 degree, so they induces some dipole moment. Here we can see tetraatomic molecule like BF3 all cancel outs, but NH3 has net dipole moment due to its pyramidal shape. And pentaatomic molecules like AB4 have zero dipole moments. That is because symmetrical tetrahedral shape of these molecules. But if any one of the atom like chlorine, hydrogen are replaced, they have some net dipole moment, as in third example, that is CHCl3. It is also used to distinguish between cis and trans isomers. The dipole moment of cis form is always greater than the trans. Used to distinguish between ortho, meta, and para isomers. Dipole moment is used to distinguish between ortho, meta, and para form. The dipole moment of ortho is the largest, then meta, then para. Determination of the possibility of resonating structure. We can also find out by the real observed net dipole moment that the compounds have different resonating structures. Both these structures of N and O are resonating structures, but the structures have high dipole moment value but small dipole moment value of N2O indicates that the actual structure is neither one and neither two but a resonance hybrid of these two structures.